Hello everyone, I'm Evan Krell and we are looking at game theoretic potential field for autonomous water surface vehicle navigation using weather forecasts. Surface vehicle planning is quite complicated. For example, here is a map of Boston Harbor whose islands are obstacles. There are also weather conditions such as wind, waves, and water currents. These forces vary over space and time and can have a substantial impact on watercraft, so shortest distance planning is not always as valuable as energy efficient planning, where an algorithm must take into account the applied force or work required along the route. A reasonable approach is to include a vector field of, for example, water currents. However, since planning is for future water currents, we are reliant on uncertain forecasts. The major theme of this presentation is to use game theory to take into account the uncertainty for worst case robust planning. In typical game theory fashion, the boat and weather are said to be opposing players in a game where the boat wants to minimize energy expenditure and the weather wants to maximize it. Of course, the real weather has no opinion, but the model allows a game theory approach for the worst case within given uncertainty bounds. Here is a quick overview of how the game theory scheme allows strategic planning. First, consider the naive boat. The goal is to travel from the purple to red circles. Inputs are a map of islands and a raster of water current vectors. The naive boat sees an opportunity to make a longer path that allows it to ride currents that are directed toward the goal. If these currents are sure to reflect reality, then this strategy is sound. The bottom image shows the water currents as they actually occur. The plan was not as effective as had been hoped. The naive boat regrets the plan since the shortest distance plan would actually have been better. However, the strategic boat is aware that these are merely predictions. The dotted arrows represent the uncertainty of the vector field, since it realizes that the bounds on the certainty are such that a worst case weather would be bad, it chooses the more conservative path. Since the actual weather is not antagonistic, it's quite possible to be over conservative with this scheme. Now let's look a little at the specific unmanned missions we are working on, since it impacts the choice of planning technique. We are working on a coastal explorer that uses online classification of underwater images to make decisions. For example, it should detect bottom features that initiate a local behavior-based path to collect data. So it may have deviated from the initial path substantially. To continue to reach the goal efficiently, it either has to replan or follow a policy from the new location. Dynamic programming based policies give an action to take from every state, which is ideal for the proposed system. The main alternative would be alternative artificial potential field, which is fast to generate, but may be very inefficient to follow. The big issue with dynamic programming based planning is the very high complexity, which makes sense since we are solving essentially all the paths instead of a single path. Many of the techniques to deal with this are concerned with limiting the search space. Here we expect to need large spaces for high-resolution coastal planning. The major contributions are a demonstration of game theoretic dynamic programming for motion planning as a means to deal with environment uncertainty. The game theoretic dynamic programming formulation has a high computational expense, but we would like to apply it to onboard robot planning. So a major theme is the feasibility of the approach using scenarios with actual water currents for Boston Harbor, specifically investigating whether the theoretical number of iterations needed for an optimal solution are actually required for reasonable approximations that would be useful for real-world planning. Notably, work has been done on the convergence of dynamic programming policies, but there was a concern that the game theory might slow convergence since both players keep changing their mind based on the changing information. A more conventional planner output is a sequence of waypoints from a start to a goal. Here, there is an action to take from every cell reachable from the goal. So a vehicle could start from any of these free locations and follow the arrows. You can see that the end result is comparable to that of artificial potential field. But here the dynamic programming solution is optimal. Using dynamic programming, the algorithm proceeds bottom up, assigning actions to reach the goal, radiating outward to assign actions to the whole reachable grid. Each cell has an associated cost. Cells around the goal have a cost of 1, those beyond a cost of 2, etc. To simplify, the diagonals have the same cost as straight moves, but the actual distance is used in the code. The point is that each cost is the cost to traverse the cell itself plus the optimal path from that action onward. Bellman optimality. So let's clarify exactly what is meant by uncertainties in this work. Basically, there is a predicted force vector available from some model, for example, the Northeast Coastal Ocean Forecast model. You can generate a vector field raster, typically for the next 48 hours with an hour between predictions, In this work, we assume that there is an estimated error bound available. Sometimes the authors of these models release error reports, or maybe the vehicle itself learns to estimate the error after repeated field trials. The actual error might force the boat to be more conservative than you need, so you could limit the error margin to just avoid highly fragile solutions. Here is how game theory is used for a single action selection as a game between the robot and weather. Each cell is the cost for a pair of actions, that of the boat and of the weather. Here the robot is shown with 4-direction movement, but actually 16 heading angles are used in the experiments. The robot can also halt with infinite cost unless it's at the goal. Here the weather is shown with 5 discrete error choices, so a mini-max solution is chosen where the player tries to limit how bad the weather can be, and the weather tries to limit how energy efficient the boat can be. An optimal solution requires multiple iterations of dynamic programming. Here the complete assignment across the map is just one iteration. Initially, all cells have max cost. After the first dynamic programming loop, the neighborhood of the goal is evaluated. In each case, the choice is between an infinite cost neighbor or a cost of 1 to reach the goal. After assigning each section, there's a working feasible motion plan, but not optimal since the games were played with incomplete information, since some neighbors are solved and some were infinite. The need for iterative dynamic programming is what makes the scheme so computationally complex. The discussion of Big O in the paper, but it's clear that the problem can get very large. Now, how do the water currents affect this? Here we have a strong southward current. After one iteration, the choice is straight against the currents at a rather high energy cost. At the time those cells were solved, the only choice was to go straight for a high cost or around for an infinite cost. The lower cost route was not known because of the order in which cells are solved, but looking at the results, it's clear that those costs of 28, 27, 26 could be drastically lowered by going around the island. And this is what happens in the second iteration. At each iteration, it may be that only the border nodes are updated, taking another iteration for 26 to be reduced. And here's an overview of the program itself. Our inputs are the region occupancy grid, water currents, or whatever force really, and errors as rasters. Currently, GeoTIFF is supported with ASCII on the way. You supply a goal location and can give a max number of iterations. We break down the system into 3 major parts. Dynamic planner really just sets everything up and controls the number of iterations of DP iteration. The main point here is that the cost to go and the motion plan, or policy, is iteratively updated by DP iteration. Within DP iteration, we initialize a first in, first out queue, add the goal location, and evaluate cells in the grid starting from the goal. Each time, we add any neighbors that have not already been assigned a cost this iteration. Actually finding the cost in the action at that space is from the Nash solver algorithm. Here, solving a 2-player zero-sum game in an iterative fashion by having the players take turn for several rounds of attempting to min or max the cost by selecting their action. Not all games have a Nash equilibrium, but this algorithm, modified from one by Raymond Hedinger, ensures that an action is always chosen. Once we halt, either by max iterations or that the motion plan is stable, the costs and plan are written to a file. Taking a brief look at the theorems, the main ideas are that eventually a global optimum results, but since it's proportional to the grid dimensions, it will take a huge number of iterations, in theory, for a high-resolution map. Second, every iteration is a feasible solution, so while it might not be optimal, each produces a usable motion plan. The question is how many iterations are needed for the motion plans to be worth using? And this question leads us to our experiments. To start, let's check that the behavior follows expectations for a simple example. First, a simple planning exercise without any currents. As one would expect, DP produces a shortest distance path. Next, those white arrows are a force against that shortest distance path, so the boat saves energy by going around the island. Next, there are currents that help the boat, so it chooses a longer path to take advantage of helpful currents instead of avoiding bad ones. And finally, we introduce the uncertain currents and generate a game theory solution. The antagonistic currents are the same as the above, but modified within an error margin. The errors are not infinite, so the boat actually still takes the longer route, but modified from before, resorting to shortest distance for the second half. And here we're just increasing the complexity to demonstrate it can solve mazes. And now here is an example using the predicted water currents for Boston Harbor. This is just a zoomed in shot from a raster over 1,000 by 1,000 cells. The energy-based behavior is clearly evident. There is a passage of lesser currents between regions of stronger currents, and the path cuts through that valley. So 20 iterations produced a path that avoids strong currents. And here we're analyzing the policy convergence over multiple iterations. The blue line corresponds to the maze, where an optimal solution was reached in only 2 iterations. The Boston Harbor data was over a much larger grid and converged in fewer than 20. This suggests that the requirement of thousands is not always needed. Over a number of similar experiments, the behavior holds. However, each iteration takes about 3 minutes with the Python implementation. 20 iterations would be acceptable for offline planning, but not for onboard unless the boat is, for example, using each iteration's plan as they are available, working with an improved path over time. And we're working on some early experiments that do this. The last result visually suggests water current aware planning, but how exactly does the game theory compare to assuming static currents? Here we see a zoomed in segment of a path with and without game theory, meaning for the one labeled DP, it's just dynamic programming with static forces. Visually matches the idea proposed at the beginning. Without considering uncertainty, a more complex path goes out of the way to take advantage of currents. With game theory, uncertainty is used so that the boat makes a more conservative path closer to a shortest distance path. Specifically, if the worst case scenario were to occur, the game theory path is 15% more efficient than the static. There's just one issue that impedes the analysis. Here I used a 0.1 error margin on the forces, but if I increase this, then the game theory solution will just get better and better at beating the non-game theory. So it's a bit too artificial to make claims with larger error margins, since we're specifically interested in real-world water currents applications. The results so far are promising since we see conservative behavior with relatively few iterations. The immediate next step is to get estimates of the uncertainty for a deeper analysis. I previously mentioned that errors are sometimes published for the models. These are not always too useful for the very localized coastal missions since they're usually just comparing to a set of ocean observation buoys rather spread out. Instead, our idea is to learn and estimate directly with the robot. So one of its duties as an autonomous explorer is then to estimate uncertainty over a time and really becoming a domain expert in its local waters. Another major future work is to improve the efficiency of a single iteration for online planning. The current implementation is in Python with a C version being written. Since the early iterations are approximate anyway, it would be appropriate to adopt approximate dynamic programming, Markov decision, process techniques, and we can use this program as a benchmark. Okay, thank you very much.